Hello. 2 minutes. There's a couple outside. I know that. Nobody likes to hang out in here. I bet. I bet. How was your Thanksgiving? You have a good Thanksgiving? Awesome. Very cool. That's all. You did it all from scratch? Sure. Yeah, go with the lattice strip. What kind was it? Apple? What kind? Nice. I mean, it was years ago. My wife is gluten intolerant and dairy and egg intolerant. So I needed it to come by, not the crust, but everything else from scratch and all the gluten pie that. And that was a real thing. Okay. It was good. It was good. My mother-in-law came into town with a small Thanksgiving with us and kids. My mother-in-law, my sister-in-law was with us. So, I did my house. I made the Thanksgiving dinner, so I did the turkey, and then we had a bunch of sides. And then standard stuff, mashed potatoes, sweet potatoes, stuffing, and it was a vegetable, I swear.
It's a vegetable pie. Sounds like a great time.
Yeah, it was a lot of fun, just kept it small. I'm more of I enjoy having large family holidays. So it was a little bit of a little different than our normal thing. We've got half the salary and it was still fun.
This in general has been an adjustment.
Yes, to say the least. To say the least. All right. 12:30. Let's get started. Lord, thank you for bringing us together this afternoon. Thank you for the previous long weekend. I pray that everybody got some rest. Pray that you help us to refocus and get through the next 3 weeks in a strong fashion. In the name we pray. Amen. Okay, so what are we doing, right? So we've got, by my calculations, we've got today and 2 more classes before our next and final exam 3, right? And that's 6 total class periods before the end of the semester. Okay, there's quite a bit that we have to do. I don't think anybody filled this out, but just in case, let's take a look. Yep, nobody took a second to fill it out. That's fine. Go to the next one. So we had a Learn Smart Do last, a couple weeks ago, I guess. There's a homework due on the 10th. That is a week from Sunday. I don't know what day that is. That's the day before the next test. There we go. All right, so homework due next Thursday. Exam 3 on the 11th, and then build and test and all that stuff, right? So I don't know if you guys saw my loud cloud message in the weekend, but there was 2 things, right? First of all, just I got back to you about the diameter, right? 10-inch diameter will fit in the test section of the wind tunnel. We have some leeway with the height because we have a stand underneath that raises and lowers. But if you stay within that 10-inch diameter, you'll be fine. You don't have to sign up with me, but we got to talk about when we're going to test this. There are classes going on where the wind tunnel is at the same time as this class. So you can't obviously break into their class period and just start using the wind tunnel. Mondays, there's no classes going on in there. Right? So it doesn't have to be that everybody from your group shows up. It can be as simple as one person from your group shows up at some point on Monday. I'll just make sure that I'm here. You tell me when you're gonna come. We'll just go in. Ideally, we don't do it at once, but it's probably better that we all have a time slot. So just let me know when you can make it. One person from each group with your bot. You take your data. What the process is. And I was trying to get one of the boxes up here to show you guys beforehand, but they're not in the prep room. And hopefully I'll have them before next class to show you. But essentially, and I'll bring in an old bot from last year that I have in my office next class. Okay. But essentially, right, you have your bot. You're going to stick it into this collar. Right? And the collar is connected to a motor. The generator and a motor are basically the same thing. It's just that when you turn the motor on, it generates. If you give it power, it creates a rotation. But if you rotate a motor physically, right, you're going to get some current. And that's what you're doing, right? You're going to put this in, attach it to the collar. Now it's rigidly attached. Wind tunnel turns on, blows air over our turbine. A turbine spins, creates some power. You can read the dial, the gauge on our box, right? The box will tell you how much voltage you get out, and I'll tell you how much resistance there is in that circuit, and then you can figure out how much power we have because power is equal to voltage times resistance squared. I'd have to look that one up. there's so many different power equations that it's hard to keep them straight. But regardless, you can look that up, right? So you'll know how fast it's going. We can talk about some of the finer points of that, but we'd like to do the test not next Monday, but the week after, which means that I need you guys to please get me files to print by ASAP, right? As soon as possible. Now, if we can't all find the time on Monday, that's fine. I'm trying to think. We can try to work around, right? But it needs to get tested at some point before you turn in your paper so that you have the data to do it. Right? So let's brainstorm and figure out a time that works for everybody. Right? It should be once it's printed and you guys put it together, right? I'm not sure. I'm trying to think if there is class. I'd have to talk and see if there's class after our class center. I think that pretty much all the rooms are in class all the time right now because COVID stuff makes it that classes have to be half the size and all that. So that Monday probably is going to work the best, but we can. There's probably a little leeway here and there. So, but yeah, try to get your designs finalized as quickly as you can. Send me the STL file and I'll forward it on to the, so send it in an email. All right, send it in an email to me. It's michael.degregorio@gcu.edu. If you don't remember that, that's fine because it's in LoudCloud, right? Go under the contact information for the professor and my email address is there. You can always private message it to me too, just to be safe. And I will then, if you're going to private message it to me, put your preferred email address in the private message so that I can CC you on the email to the printing people so that you know. Typically what happens is they'll print it and they'll put it in the back room over here and then I'll give it to you. It takes a couple of days, obviously, to get through their process. So the sooner that you get your design finalized and get me the STL files, the faster you get your print, the sooner that you can build it, the sooner that we can potentially test it, right? Okay. Cool.
You have to have a specific version of SolidWorks.
As long as you export it as a .stl, it doesn't matter. STL files never go out with age. Right? And honestly, if you had, this is totally an aside, but if you had a .stl file, you could import your SolidWorks into MATLAB. Just based on what it basically converts your entire file into what amounts to a text file and allows you to import it to places where you didn't really think you could have SolidWorks. But we're not going to do anything with that. That's just for your information, really. But if you get me an STL, that's all they need to print it, right? And if they start giving us crap, I know a place where we can print them that doesn't have very high volume, but let's go through the proper channels first. Okay. All right. So you guys have any questions on the CLC stuff? Because I know that there's a lot going on. So let's just kind of review, right? The build and test is what it sounds like. You are going to build your thing, your vault, and you're going to test it, right? Unless it breaks, you'll get basically full points for the build and test, right? The build and test is all about, I built it, I tested it, I got my data, right? It didn't fall apart, okay? The design is your actual paper, right? The design is due, all these things are due. I think I put it on the 18th, whatever it says in LoudCloud. LoudCloud is correct, okay? Whatever it says in LoudCloud, right, we're gonna do, oh yeah, it is the 18th because 18th is the last day of actual physical class and you guys are gonna do your presentations on the last day of class, right? And so do your presentation and then turn in your paper that night, right? And then we're done for the semester, that's it. All the grades will be in at that point. Okay, you guys have any questions on the vault stuff? Things specific right now. You come up with anything ask after class, or I've got office hours from 3 to 5 today, right? So we can do that. Okay. So we're in crunch time now, right? It's the last 3 weeks. We don't have very many classes left, and just need to push through. This is basically, this should be all the assignments that are left for class, right? Right here. This should be everything. If I missed something, I apologize, but I think that's correct. All right. So today, right, last class, what did we do, right? In the sense for recap, right? What did we do last class? It's been a while. So we went over impacts and momentum impact, momentum impulse, and we went over work energy, right? That's what we did. And we're gonna do a couple of problems involving that. But we're also gonna watch a video that I think is really interesting that is actually pretty long, so I split it in half. We'll watch the first half at the beginning of class after we do a problem? No, we'll watch it right now. Watch the first half, then we'll watch the second half at the end. Okay? All right. Assuming that the internet allows me to put it in. No. Video no longer exists. There we go.
Hey, Vsauce, Michael here. If every single one of us held hands together in a chain of unity around Earth, would there be enough of us to go all the way around the planet? There are about 7.5 billion of us, and that's a lot. But remember that many human bodies thrown together into one big pile would barely fill the Grand Canyon. This is all of us in one place. The physical bulk of all living human flesh on Earth today would only make a cone about 7,000 people tall and 2,000 across. That's it. But that's a three-dimensional shape. What if we made a one-dimensional, single-file line of people, each with, say, 1 meter of room, and we stretched that around the planet? Well, we would make it all the way around and still have 99.5% of the human population left. If we made a circle that included everyone, the ring of people would be more than 2.4 million kilometers in diameter, dwarfing the orbit of our own moon. Now that's not just a circle, that is a circle. Let's talk about circles today, specifically something that they do, roll. Well, what is rolling? Well, rolling occurs whenever something moves with respect to something else and is always in contact with that something else. And the contact points have instantaneous velocities of 0. That is, there's no sliding. In mathematics, the path traced by a point on a rolling object is called a roulette, French for little wheel. The center of a disk produces a roulette that's just a smooth, straight line while rolling on one. And this is why disks are good wheels. A square, on the other hand, would be bumpy. But square centers can make straight, smooth roulettes across the right surfaces. This is the principle behind square wheels, which I recently had the pleasure of enjoying at the Museum of Mathematics in New York City. Stan Wagon wrote a fantastic and famous article about wheels, which I've linked down in the description below. It's a great read. He also contributed a fantastic interactive tool to the Wolfram demonstration project that allows you to build a wheel and then find the corresponding road shape that allows it to roll smoothly. The roulette traced by a point on a disc as it rolls on a straight line has a special name. It's called a trochoid, from the Greek word for wheel, trochos. Now, trochoids can be curtate or prolate, depending on whether the tracing point is inside or outside the circumference. If the point is on the circumference, the resulting curve is called a cycloid. Cycloids are very special, and they are the star of this episode. Now, I've been working with Adam Savage a lot lately as we gear up for Brain Candy Live, our 40 city tour that I hope to see you at. Recently, I asked Adam for some help with roulettes. Adam, do you have a favorite polygon?
Literally an actual.
You can't go like your children. You have a favorite. I don't have a favorite. I do have a favorite thing that you can do with a polygon.
Okay.
Make a cyclogon.
A cycle.
Yeah.
A cyclogon is an actual thing.
Yeah, it's an actual thing. It's an actual thing. Do we have a polygon around here? Here, this here's a square, right?
Right.
Say this is a square. If I take one of the vertexes of this square, and I start rolling this square, and you follow where that vertex, oh shoot, let me roll this better. Are you ready? All right, the actual path
Describes a curve.
described here, yeah, that curve is called a cyclogon. And as you pick polygons with more and more sides, you get closer and closer to what I want from you today. A cycle. A cycle. Now, I could have just done this in Photoshop and done like an animation like I normally do, but you have a shop
We can actually build.
and you can build things. Why do I want to build a cycle? Well, let me ask you this. With only gravity to move you, what's the fastest way to roll or slide from a point to some other point below, but not directly below? Would it be a straight line? Well, that would certainly be the shortest path. But when you fall, gravity accelerates you, and falling vertically a lot right away would mean having a higher top speed during more of the journey. And that can more than make up for the fact that a path like this is much longer than a straight line. But of these two considerations, accelerate quickly and don't have too long of a path, what's the optimal combination? Finding the answer, the path of least time, is called the Brachistochrone problem. And it's been around for a while. Galileo thought the answer was a path that's just a piece of a circle. But he was wrong. There's a better one. And in 1697, Johann Bernoulli came up with the answer using a very clever approach. To see how he solved it, let's start with a similar problem. You are standing in some mud, and you want to run to a wall in the street as quickly as possible. Now, a straight line would be the path of shortest distance. But if you can run on pavement much faster than you can run in mud, the path of shortest time would be one in which you spend less time moving slowly in mud and more time on a surface you're fast on. The angle you should enter the pavement at depends on how fast you move on both surfaces. As it turns out, when the ratio between the sides of these two angles equals the ratio between your speeds across both surfaces, the resulting path will be the optimal quickest route. This is called Snell's law. Light always obeys Snell's law. When it changes speeds, like when it leaves a material in which it moves more slowly, like water, and enters one in which it moves more quickly, like air, it always refracts according to Snell's law. In other words, light always follows the route that is the fastest for it to take. Bernoulli used this fact to tackle the Brachistochrone problem. Light changing in speed is analogous to a falling object changing speed. But of course, a falling object doesn't just speed up once. Its speed is always increasing, it's accelerating. To mimic this, using light, which Bernoulli knew would always show him the fastest possible route, all he had to do was add more and more thinner and thinner layers in which the speed of light was faster and faster and faster. And, well, what do you know? There it is, the Brachistochrone curve, the path of least time. Roll down a track like this, and you will beat anything rolling down any other path every time. Bernoulli was clever enough to realize that this curve can be described in another way, as a roulette. Specifically, he noticed that it was a cycle, the path traced by a point on a circle rolling along a line. A cycling satisfies Snell's law everywhere. To see why, I highly recommend watching this video on the Brachistochrone problem. This channel is fantastic, by the way. I'm a huge fan. The visuals and explanations are top-notch. Anyway, a cycloid provides the perfect balance between keeping the journey distance short and picking up speed early. Now, I told Adam all of this And I told him that it would be really fun to have a cycloid curve we could roll things down. And he said,
Clearly, we should start building.
we should just start building it. What we need is a circle.
Okay.
That's the height that we want. And then we're going to use that circle to trace and mount
A
a
cycloid
cycloid
curve. I want to do a race, right? So
Yeah.
if we're gonna do, like, if you have point A here and point B here, and you say that there's some kind of curve that's better than a straight line in terms of something traveling between those two, then I want to also make a straight line from A to B.
Yeah, and maybe also a really extreme curve, like that.
Right, okay. Let's see. Protractors there. Ooh.
You have a compass extension.
I do. I have all sorts of.
I've never seen such a thing. Is that it?
Yeah. That connects to that. That connects to that. That's gonna be great. Okay.
I almost am feel guilty that this is like a dream of mine coming true.
Oh, really?
But it's such a nerdy dream too. It's not like I want this, you know, red line baby gun. It's like I just want a curve that things roll down.
Okay, so then clearly when we're done with this is my Christmas present. I think I'm currently like working out a way to do this in my head that actually makes it fairly compact and not super complicated.
Yeah.
Take a blade and cut out like an inch around this whole thing.
How are you gonna do the finishing?
I'm going to cut this, unless you would like to, on the back.
You can start.
Okay. Okay. Now, that's a little bit rough, so we're going to finish it on like this.
Oh wow. That's close enough. It's pretty good, yeah.
So now we want to use this to draw a cycloid.
Yeah.
So you'll need a little hole.
That's what, yeah, so that the point of our drawing implement is on the rim, not above it.
Use right inside. No, I messed that up.
I don't think so. It is, yeah,
That's all right.
that's even better than having the rim hold, because we want the line to be right on the edge.
Okay, so what we're going to do is we're going to create a pattern for the cycloid curve that I'm then going to transfer to a curve to clear the curve. Right? Allow us to see things really clearly.
Yeah.
So, this allows me, right, clear cycloid, right? So it is literally like that, right?
Oh yeah, see, this is perfect, yeah.
Pushed against here, I shouldn't slip.
This is like a Ouija board for geometry nerds.
It is a Ouija board for geometry nerds. Okay, there we go. That's
Show out Wikistachrome.
That's
That's
the curve that we're talking about.
Yeah.
That's the beginning, that's the end, and this is our pattern.
Yeah. That's cool.
Okay. So
I'm gonna end up with
let's say 3/4 of an inch thick. It's going to have channels. Table saw out of it that travel its length, and in those channels will sit and clear acrylic curves. And then it'll also have an upright that also will have channels milled out of it on the table saw. And that will allow the curve to sit and be supported.
yeah, a little backstop here at the bottom. That'll allow us to hear that they all hit at the same time.
there's a couple things going on. One is that we've got cycloid, straight line,
and then we've got extreme curve.
Right, and are these, you had mentioned bending the acrylic so we can adjust the.
No, actually, I have, and this is, you'll like this. So
Okay.
the acrylic will just be a thin acrylic, just a thin sheet of it.
Traveling on that will be, I'm gonna have material for this. Some Delring or sealed rollers that look like this. So from the side, they'll look like this. They'll look like an H, in which the acrylic sits in there.
And the roller is self-supporting on the acrylic, it rolls down.
Ah, that's tolerance.
Love
They like those curves. While I don't want to realize cycling track, let's take some time to appreciate other kinds of legs. As mentioned before, short blades are curves made by a disc.
All right, pause it there. We'll go back into it, right? So what is the whole point of this? Why are we watching this video, right? Why are we watching it? Does this have to do with anything that we've talked about so far? Well, it does. It has to do with kinematics, right? Because it's about the path that you're traveling. So there are certain paths that are actually faster than others. Everybody's always high on straight lines, right? It's the shortest point between two things, but it might not be the fastest way to get there. And we've shown it mathematically, but what we're going to see in the end of this video is the physical representation of how a bacrystochrone actually is faster than a straight line and this really extreme curve, right? So we'll get back to that later, but before we do that, let's do some problems, right? So what do I have here, right? This device is an assistive device that helps people in wheelchairs swing a baseball bat. Right, that's essentially what it's supposed to be used for. So imagine for a section, and I don't like calling position one where it's cocked, but whatever, it doesn't matter what we call position one and position two. So what happens, right, is you pull the bat back, right? So a baseball attachment that helps people with mobility impairments play t-ball and baseball is powered by a spring that is unstretched at position two. So as you can imagine, the way that this would work is you would take the bat from position two, pull it back into position one, right? And then you would let it go. Right? When you let it go, the bat swings and it hits the ball, right? And for T-ball, that's awesome, right? It should hit every time. If you're playing baseball, then there's a little bit more timing that has to go along with it. The spring is attached to a cord that is fastened to point B on a 75 millimeter radius pulley. The pulley is fixed at point O, and it rotates backwards to the cock position at theta is equal to 120 degrees. The rope wraps around the pulley and stretches the spring with a stiffness of K is equal to 2,000 Newton per meter. All right, so let's unpack the first part of this. What is going on? So you see this spring here. That's one side is attached to the wall, the other side is attached to a spring or to a string. The string wraps around the pulley. So as I move this pulley, right, because the bat's attached to the pulley, as I move the bat, the pulley rotates. It's going to rotate through an angle of theta. And because of that, this string will travel the circumference of the circle, right? So it's going to travel some linear distance, which is going to stretch that spring by some linear distance, okay? The combined mass moment of inertia of all the rotating components about point O is 0.40 kilogram meters squared. Right. So we're also told the combined mass moment of inertia. Remember, we talked about I sub G or I bar, and we talked about I sub O. What happens if we're rotating about a point that is not the center of gravity? We need I sub O. We are given I sub O right off the bat here. We're given it. The swing is timed perfectly to strike a 145 gram baseball traveling with a speed of V naught is equal to 10 meters per second at a distance of h is equal to 0.7 meters away from point O. Knowing that the coefficient of restitution between the bat and the ball is 0.59, you need to determine the velocity of the baseball immediately after impact. Assume that the ball is traveling primarily in the horizontal plane and that the spin is negligible. Right, so there's a lot going on here, right? And this is a really good problem because it does a lot of things. So what are we asked to find? We're asked to find what happens after the collision, right? How fast is the ball moving after we hit it with the bat? Okay? But in order for, all right, so that's obviously a momentum problem, right? Because it's a collision. And whenever we have a collision, we're automatically going to think momentum, right? And momentum tells us that the sum of my linear momentum initial plus the sum of my impulses, right, is equal to the sum of my final linear momentum, right? Are we going to have to deal with angular? I'm not sure, but we'll write down the equation anyway. Right, this is just my angular momentum equation. Right, well, it tells us that this is traveling primarily in the horizontal plane, right? So we would assume that it's mostly linear momentum that we'll have to deal with. And linear momentum is m times v, right? It's m times v. But what we don't know is how fast is the bat traveling before impact. That's what we don't know. We know how fast the ball is traveling. So how are we going to figure out how fast the bat is moving when it hits the ball? And that way we're going to figure that out is from work energy, right? Because all of my kinetic energy, right? So the sum, so if we write down our work energy equation, and we're not told that there's any frictional losses here, right? So we're going to ignore them. We're going to use conservation of energy. And that tells us that our kinetic energy initial plus our potential energy initial is equal to our kinetic energy in state 2 plus the potential energy at state 2, right? And this is a general form. So we were asked, we started at the end. What we're asked to find? We're asked to find the velocity of the ball after impact. We know that to do that, we are going to need impulse and momentum in some way. Yeah, Zach.
What's that?
H is angular momentum. H is angular momentum. We know that we're going to need the velocity of the bat to figure out what the final velocity of the ball is, right? In order to get the initial velocity of the bat, or let's think of it this way, the velocity of the bat right before impact, we need to use conservation of energy to figure out, I need to get from here to here, right? I need to get from position 1 to position 2. How fast am I moving? How fast is the bat moving in position 2? Right? Well, it's going to be moving as fast as we figure it out. It is from here. Once we know how fast the bat is moving in position 2, we can use momentum and impulse to figure out how fast the ball is moving. Now, what we should expect as a result here is that the ball will change direction, right? Because we've all either played or seen a baseball game before, and we know that when you hit the baseball with the bat, it changes the direction. I mean, I guess it's possible that you could throw it fast enough that the bat would change direction and the ball would keep going, but I mean, very unlikely. Very unlikely. All right, anyway, so this is a combined problem, right? We need to use impulse and momentum and work energy all together to get everything done. The only thing that it doesn't test is Newton's second law, right? Because we're not asked for any forces or anything. But I mean, I guess if we really wanted to, you could ask for the reaction forces at the pin O, but we're not going to do that because we're just not going to do that. Okay. So here we are, right? We've got this. So how do we do this? What do we do first, right? So we think it through. I would highly recommend that if you're reading a problem like this, think about what you need to end up with, and think about what are the things that you need to get to that final state, right? So we started at the end and we worked our way back, right? Like Michael Scott's 100-day plan, right? Day 100, we saved the company. Day 99, what did we do, right? It's kind of like that. All right. Okay. So what do we do? Well, if we're going to start with conservation of energy, let's start with our state diagram here, right? And I have flipped in my head position 1 and position 2. Okay, I understand that it said in the diagram that position 2 was when it was cocked and position 1 was not. Okay, well, just bear with me. Right? So my diagram, I've got both of these things, right? I've got my position 1 and position 2. I've got it when it's horizontal, and I've got it when I pull it back by 120 degrees. Okay. I've got that spring. I know that R for the pulley is 0.075 meters. I know that K is 2,000 Newton per meter. Right. I have this angle up here, alpha, in the top left corner. I also have this length, H. H is the length of the bat. Were we given H in the problem statement? All right, let's just look real quick. Yeah, 0.7 meters. It's right here. I'm given H. Given quite a bit of information here, right? So we're going to want to draw this first. I would say, if you guys feel comfortable doing this problem, you will feel comfortable with anything else that can be drawn at you. That's what I will say. Okay. So are we okay with the diagram? Is everybody following why we have this diagram the way that we do, right? Remember, this is a work energy problem to start with. It's a conservation of energy problem. So we need to draw it in state 1 and state 2 because we're going to compare these two things. We also have to set a datum. Now, for us here, remember, work energy is scalar. So it doesn't matter if it's linear or rotational. What matters is the total amount. So we're not writing one of these in terms of X and Y, right? We're not writing one of these in terms of linear and angular. We're just going to mass all of our energy together. So when we have our equations, right, we need to take care of the total kinetic energy in the green state, and the total kinetic energy in the pink state, and the total potential energy in the green state, and the total potential energy in the pink state. Okay. So we know that this starts from rest. And this is where my numbers are not going to line up with this, right? So well, hold on. Yeah, no, I have this. This is state 1. Position 2 is state 1. That's why this is confusing. The way that it's written. Position 2 is state 1. When I pull it back, right? When I pull it back and it's cocked, and I'm holding it, that is state 1. It starts from rest because I'm holding it, right? I've got this. I almost want to build one of these just to have it as a reference, right? But imagine you're pulling this thing back, right, and you're holding it, and that's the starting position, right? So we're starting from rest, so we have no kinetic energy. Remember, the book uses T as kinetic energy and V as potential energy because reasons. So to start off, I have no kinetic energy, but my potential energy, if this is built correctly, I won't have any dipping, right? This will work. Remember, I'm looking at this from the top. So the potential energy due to gravity is 0, right? This shouldn't be raising and lowering as I swim. So I only have a less elastic potential. An elastic potential is equal to 1/2 kx squared, right? Because I have a spring, and that's what spring energy is equal to. Right, well, I know K was 2,000. And I know X, kind of. X is what? How much distance am I traveling? How much is this spring gonna, right? So this spring is going to expand, right? As what happens? Because remember, it's tied around here. So at some, let me do it this way. Let's draw it this way. So here's my pulley. And we start at point B, which is here, and this is my unstretched spring length, right? That's point B. As I rotate this, right, and remember, this is attached to a string here. As I rotate it to this position, right, B, that's going to pull this string here, which is going to open up our spring there, right? So it's stretched our spring. And I know I've drawn this horribly, right? But the idea here is that, let's try that one more time. I'll try to draw it up here. Right, so this spring is now expanded, right? It's expanded. How much has it expanded? Well, it's got to move by the same amount that we moved the string. How much did the string move? Well, the string followed the curve of the circle, right? And that means that it's equal to the arc. Well, the arc on a circle is just r times theta, right? We know r and we know theta. We know how much angle we've moved through. It's given. So we know x. Right? X is going to be 0.075 times theta. Okay, now I haven't plugged theta in yet. Okay, and that's squared. What about at T2? Well, at state 2, I have rotational kinetic energy. I do not have any linear kinetic energy. Why? Because we're doing everything about point O, and point O doesn't move, right? Point O doesn't move, but we rotate around point O. So there's no kinetic energy linearly from point O, but there is rotational energy based off the combined inertia of everything. And I sub O was given. And at state 2 here, in the pink state, the spring is also not pressed anymore, right? Or extended. Yes, Zach.
So that T
T is kinetic, right? So remember, in the book, the notation that the book uses is that T is equal to kinetic energy and V is equal to potential energy. And potential energy for us has two flavors, right? It's got elastic or gravitational. Gravitational only changes if we're changing the height. Elastic only applies if we have springs. So in the pink state, we have no spring energy, right? Because now we're back to the original position for B, and the spring doesn't move. So we can apply conservation of energy. We can say the potential energy at state 1 has to equal the kinetic energy at state 2, right? I know everything in this equation except for omega 2, right? So I can figure that out in a moment. Everybody okay with this so far? Maybe not. Yeah. If we can walk through this problem and we can understand how to do it, it evaluates a lot of concepts, right? If you can think your way through this one, you should be able to think your way through anything else that the book throws at you. All right. All right, so we're good so far. We have any questions so far? Woo. My fingers fell off. Jeez. All right. Everybody's okay. So we plug some things in. I know all the things, I'll plug them in. I have to find theta. It says you have to find theta, but we were given theta, right? We were given theta. We don't have to worry about that. But we do have to put it into radians. And so these equations want everything in radians. Right? So how do we go from radians, or from degrees to radians? Multiply by pi, divide by 180. Right. So we get 2.09. We plug that into this equation up here. And hey, this is what we're left with. And we can solve this for omega 2. And we'll find out that omega 2 is negative 11.08 radians per second. Right? That just means that it's going clockwise. That's all that means. So if I wanted the velocity of the bat itself, specifically the velocity of the point where the bat is going to be hitting, right, the ball, which was h away. This is omega 2 times h, which is 7.76 meters per second. Right? This is the big thing. So remember, the bat, right? Let's draw it. Let's draw it. And so here's my baseball bat. I know. It needs more taper. I know. There, that looks more like a baseball bat. Here's my baseball bat. The ball is here, and it's going to hit at this point, which we know is a distance h away from where we're rotating, right? So if I want to know how fast the bat is traveling when it hits the ball, I need to know how fast it's moving at that point, at the contact point, right? And we're going to say that contact point, since it's h away, has a velocity or a tangential velocity at that point of omega times h. We know omega, we know h, so we know the velocity of the bat, or what I've called V2 bat. Are there any questions on this one?
So where did the 30-degree angle come from?
Don't worry about that. So that's a holdover from a different way that the problem was posed. And then instead of doing that, I decided we should just give the 120. So a couple of things has to happen, right? So we can talk about that 30. If you weren't given an angle, could you figure out what the angle is, right? If you weren't given what theta is, right? Well, yes, you can, because if you draw this triangle here, right? You know the length of the legs. You should be able to figure out using log sines and log cosines what the angles are. Right? You know, you have h and h, right? So since they both have the same length, you know it has to be an isosceles triangle, right? So it's just more geometry. This isn't really a class about me testing how much geometry you can do. I mean, it's great if you can do it. But if you have to do a problem like this, I'm just going to give you the angle. Right. Okay. But that comes from the fact that it's an isosceles triangle, so you can figure out what alpha is. Then once you figure out what alpha is, you know the other angle also has to be alpha because the two lengths have the same length. Right? The two legs have the same length. And so 180 minus twice times alpha gives you what theta is, right? Which is what we did here. Okay. But we were told it was 120 to begin with, so it doesn't really matter. Okay. Any questions? Any other questions? No, we good? Yeah, let me see.
When did you say this is going to replace it?
After class today. Yeah. That's what I'm doing up here at the end of class. Logan caught me the other day when it said not safe for children or whatever. Yeah, that's what I was doing. I just posted it right after. And this isn't safe for children. If any of your children are watching this right now, stop right now. It's not appropriate. All right, anyway. Okay. Any other questions? Are you all right so far? Yeah. Stepping through. Okay. So we did the work energy. I figured out how I got from top back to right before impact, right? So this is right before impact. And I know the velocity of the ball right before impact. I also know the velocity of the ball right before impact because we were told what the velocity of the ball was right before impact. Right, so we can draw my impulse momentum diagram. Right, so I have my impulse momentum diagram. And I don't need the MBAT, VBAT. I need either one or the other. Right? Dr. D goofed on his diagram. We'll talk about it in a second. Right? But I've got linear momentum, MB, V naught, right? Mass of the ball, V naught. I was told the mass of the ball in the problem statement. It's listed up there in the top corner as 0.145 kilograms. I know V naught, that was 10 meters per second. So in my initial state, I've got M, B, V, V. I've got MBAT, VBAT, or I naught, I sub O, omega t, plus the summation of all of my impulses. But because this is a collision, right, I know that the impulsive forces are going to cancel each other out here. So we don't have any impulses. And in the final spot, we will have MBAT, VBAT prime, and MB, V ball prime, V2 prime, I think I wrote it as. All right, so what's going to happen in the second condition? The bat's going to continue forward, but the ball is also going to change direction. Right? So this should indicate to us right off that the mass of the bat should be significantly more than the mass of the ball, right? So we should have more momentum from the bat than we have from the ball. That's what's going to have this net change in momentum. So it turns out that this is a conservation of linear momentum problem, right? And we get that from drawing just linear momentum. What about the angular momentum? Does angular momentum come into play here? No, it doesn't. And why doesn't it? Well, it doesn't because we are interested in finding the translational velocity. So we have two unknowns here, right? I've got VBAT and V2, right? So state 2 is completely a mystery. I know things about state 1, but I don't know enough about state 2. I'm going to need two equations here, right? Because I have two unknowns. But conservation of momentum is only going to give me one, so I'm going to have to use coefficient of restitution. And the coefficient of restitution was given to me. It's 0.59. The equation for coefficient of restitution is the final velocity of the bat minus the final velocity of the ball divided by the initial velocity of the ball minus the initial velocity of the bat. Right? And looking at that, I only know two of them. I only know two things. I know V bat and I know V ball, but I don't know V prime bat and I don't know V prime ball. But I can say that 10 minus 7.75 is 2 1/4. And if I multiply 2 1/4 by 0.59, right, I'll get 1.3275. Right, so I just simplified this equation. Right, and that's one equation. Now you see that omega 3 is V prime bat over H. Sure.
So the 7.75 is what we got from the 11.08.
Yes. Yes, sir. So that's the initial, so that's the velocity of the bat right before impact. The velocity of the bat right before impact. Remember, you're going to have all these equations on the equation sheet, right? So basically all the equations we had last time. Well, 2 quizzes ago.
Why is the second emergence number, why they have to flip that minus ball over ball minus that?
Good question. So the way that coefficient of restitution plays out, right, remember, is that it's the relative velocity of these two things, right? And the reason that we flip them has to do with how we derive it. So when we derived it, it came from two parts, right? There's the deformation portion of it and there's the restitution portion of it. And depending on which side you derive it from, you will start with, how do I say this? So think of it this way, right? It's the relative velocity of the final over the relative velocity initial, right? So in the initial state before impact, we subtract the ball from the bat because, so this is the other thing about this. It doesn't matter which one you put first, but you do have to have them staggered. Okay, so if you had bat V prime ball minus V prime bat, it would have to be staggered the other way. And the reason is we're assuming that one of these is going to be moving faster than the other at the beginning. So it's essentially it's just a way of us keeping track of our negative signs, really. So it's always final minus initial, or final minus final over initial minus initial, but you have to stagger which particle or which body you're talking about. It says there omega 3 is V bat, V prime bat over H, and that'll come into play in a minute. It doesn't right now. Okay. So we still don't know the mass of the bat, though, right? We were never told what the mass of a bat was. And that seems problematic. All right. Do we have any other questions on here? Okay. Tracking. All right. So what did we do so far, right? For momentum and impulse momentum. Draw our diagram and we write our equations, right? We only talked about linear momentum so far, and that's fine. But we came up with this equation, which relates the final velocity of the bat to the final velocity of the ball. Now we're going to talk about angular momentum. Because in fact, Dr. D, you said we didn't need it before. Well, that was before. This is now. So we do need angular momentum. Why? Angular momentum is going to give us a way of relating I sub O omega 2. Okay? Because remember, we don't have the mass of the bat. Right? We don't know the mass of the bat, but I know the combined moment of inertia of O. And I know the distance that everything is from O. So if I sum my angular momentum about point O, I'd sum my angular momentum about point O, plus the sum of my impulses about point O, which is going to be 0, is equal to the sum. This is initial and final. So initially, how much angular momentum do I have? Well, from the ball, I've got mass of the ball times the velocity, right, times h, which is the distance I am away from O, the perpendicular distance. I add to that I-O omega 2. Right? We know, we can figure out what omega, actually, we know omega 2. Right? We figured it out in the last problem, last part of the problem. This is equal to negative mb v prime ball times h minus I-O, that's omega 3, right? And this is why we wrote down the omega 3 equation. Because I can write omega 3 in terms of v prime bat. And see, now what happens is now I've got two equations. Now I've got two equations that allow me to solve for the two unknowns. So what do I've got? I know mass of the bat, 0.145. I know the velocity initial of the ball is 10. And I know the distance h is 0.7. I know I and I know omega 2. I know everything in this equation except v prime ball and v prime bat. But I can plug in my expression from here, right? Because if I rewrite this, isn't v prime bat just equal to 1.3275 plus v prime ball? Which is what I wrote. So I have to combine those two things. If I combine those two things, I now have one equation that I can solve algebraically for v prime ball, which is what I was asked for. And it turns out that directly after impact, this will be moving at 3.95 feet per second. And if I wanted to, I could find the velocity of the bat after impact too, right? Because I just add 1.3275 to that. So it's a little bit sloppy the way that Dr. D walked through the last part, right? So let's refresh. Why do we need angular momentum? If you're not given the mass of the bat, you need a way to figure out what the mass of the bat is. It's not going to be easy for, like, could you? Yes, you could figure out what the mass of the bat is, but you were not given enough information to do so here. How would you? Well, you would need to know the mass moment of inertia of the center of gravity of the bat. You need to know the shape of the bat, right? You need to know the actual, a lot of things. We don't need those things because we have I sub O. If we know a little bit about rotational kinematics, specifically that omega is equal to v divided by the perpendicular distance that I am away from the center of rotation, I can turn angular momentum into an equation that is dependent on the translational velocity. And before you guys ask, yes, all the Hall of Fame baseball players do this calculation in their head before they take a step. That's why it takes so long to get out of the batter's box sometimes. You can't get in there before you do your math. They pretend like they're swinging, taking practice swings, but it's really a mental game. It's all up here. Okay. You have any questions on this one?
See how we got the ball velocity of that one.
So remember, from this slide here, right, we've got 1.3275. Let me write that so people can actually read it. 1.3275 plus V prime ball is equal to V prime bat, right? That's just me rearranging this equation in the box. And so then I plug this value into here. I'll get that. Okay. Now, do you need to find the velocity of the bat for this problem? No, you were asked for the velocity of the ball. So, did it take you that much longer to find the velocity of the bat? No. That's fine. Could we now use what we know to find the mass of the bat? Yeah, you would go back to your linear momentum equation. Plug in V bat and V ball. Solve for M. Do you need to do that? No. Don't ask for that. Any other questions? No? Nothing? Okay. Well then, I got this for you guys to try. Why don't we take like 45 minutes? I want you guys to try to work through this, right? So what is this? Two solid spheres, each having a radius of 3 inches and weighing 2 pounds, right? So it's a weight, it's force, it's not a mass. Are mounted on a spinning horizontal rod that has a mass moment of inertia of 0.25 pound-feet a second squared. And omega, right, and an angular velocity of 6 radians per second, as shown. The balls are held together by a string, and then somebody comes along and cuts that string. We want to find the angular velocity of the rod after the balls have moved to points A prime and B prime, right? So once they've moved to the end stops here. And B, we want to know how much energy is lost due to the plastic impact of the spheres and the stops, right? So there's a couple of things I want to draw your attention to. First of all, we know, all right, so first of all, before you guys get started on working on this, right, what kind of problem is this? What should we be aiming to do here? What are we being asked for? What are we being asked for? You're gonna figure out what kind of problem it is. You've got 3 things in your toolbox. And you've got Newton's second law. Good old Newton. And Newton is going to ask you about forces and acceleration. Right? That's Newton. Should we be using Newton for this? Yes, no. Yes or no? Who thinks yes? Who thinks no? No's are good, right? That's Newton. Now we've got work energy. Work energy is typically going to ask us for forces, displacements, and velocities. Typically. So is this a work energy problem? Are we going to ask for forces, displacements, and or velocities? Who thinks it's work energy? Yeah. Who thinks yes? Right? Who thinks no? I mean, Miguel, you're not wrong. Right? Part B is specifically asking you for the energy, so you're going to probably need it for at least part B, right? And the final type that we have is momentum impulse. And this is going to, this is for time, forces, or velocity, right? So who thinks that this is impulse momentum? We got one who thinks it's not impulse momentum. So far, the one thing that we've mostly agreed on is that it's not Newton. And I guess that's good because that gives you a 50-50 shot, right? Part B is definitely an energy problem because it asks you specifically to determine the energy lost, right? And part A asks you for angular velocity after the rods have moved to A and A prime and B prime. And Miguel is right. It is. It's momentum impulse, right? Why is that momentum impulse? Because when it hits those end stops, it's a collision. Also, right, the sentence plastic impact is used, which lets us know another thing, right? That's going to tell us and informs us about a coefficient of restitution. If you have a plastic impact, you guys remember what the coefficient of restitution is for a plastic impact. Do we remember? No. Give you a 50-50 shot. It's either 1 or 0. Who thinks it's 1? What is coefficient of restitution a measure of, right? It's a measure of how much energy is conserved, essentially, during a collision. How much energy is transferred? Yeah, Zach.
Wasn't one sort of like perfect and therefore physically impossible?
Yes. 1 means that you have a perfect transfer of energy. And that is a perfectly elastic collision, right? Because all of the energy will essentially be conserved. We know that this is not the case in real life, right? Because energy is released during an impact via sound impulse. However, a plastic impact is completely realistic in real life. A plastic impact means that we have deformed and that now the two bodies are essentially combined as one body. This is like a really high-speed car accident where you have two cars that got so damaged that it's as if they're just one chunk of metal, right? And that's going to be 0. Plastic impact doesn't transfer, the energy doesn't transfer. All the energy goes into deforming the bodies. Okay? All right, so I guess, we'll just walk through it. We'll just walk through this one together, right? Instead of taking the time to do it. Is that okay? You guys want to do it? I feel like you don't want to do it. All right, so we've determined from the problem statement that we're probably going to have to apply both of these at some point, but not you, right? Everybody who's cool and understands that. But what are the key words that you want to pick up on here? Energy loss and plastic impact. These inform us that we are likely going to have to do work energy. Remember, if energy is lost, it's probably not conservation of energy. So you're actually going to have to do the work energy problem, right? So let's see what we do, right? I would like the next slide, please. Thank you, PowerPoint. All right, so we talked about this, right? It says type is momentum impulse. And for most of the problem, we are going to work through momentum impulse, right? What do we know? We should always write down what we know. The radius, right, r sub s, the radius of the sphere. Each of those balls has a radius of 3 inches. Each of them weighs 2 pounds. The mass moment of inertia of the rod was given as 0.2516 feet per second squared. We know that omega is 6 radians per second to start with. And what we want to find is how fast is the rod moving after the ball moving to the prime location, and we want to know how much energy is lost due to a plastic impact, and plastic is in all caps. So since it's momentum impulse, what are we going to do? We'll draw our momentum impulse diagram. Right? This has both. This is combined. Right? This is my combined impulse momentum diagram that shows everything that we need for translational momentum, but also rotational momentum. Okay? So what do I have? In the starting position, both of these balls are going to have some translational velocity at this moment in time. Right? Both of them also have I sub s times omega 1, right? They're both rotating, right? They're rotating about that center R. Okay?
What's the WS?
Omega or WS, that's the weight of the spheres, the weight of the balls. That was given in the problem statement. Each one weighs 2 pounds. It's a pretty hefty system. We're really lucky to find one on Craigslist. That's the problem title. All right. So this has everything right, and this entire rod is moving with I sub r times omega 1. Right, so all of these are rotating with the same omega, right? And I think that makes sense. If you're looking at this rotating, at this moment in time, they all have the same omega, and they should all have the same omega because they're all rotating about this point R. I also have these impulses here, the reactions. I have the reactions at point R. And the integral of r sub x dt, and the integral of r sub y dt. Now that's not going to be a problem for us, but we have to draw them anyway. Why is it not going to be a problem for us? Well, because we're probably going to take the angular momentum about that point, and they'll just go away, right? But there are forces there that we have to recognize in case we need to look at momentum. And then finally, in state 2, this has moved, right? Now the balls are at the end stops. They've hit. It's a plastic collision, so they've stopped moving essentially. And I've got some tangential velocity for each of the balls here, and they're still going to have some omega 2, and this is still going to have some RR omega 2. There's a couple of things that we weren't given, right? We weren't told what is the moment of inertia of the sphere, right? And it looks like we're going to need it. So we're going to have to look up what the moment of inertia equation is for a sphere at some point. Is everybody cool with this diagram? Yeah? Remember, right, and tell everybody who takes this class the same thing. if you don't do anything else, right? If you are super stuck and you read the problem statement and you don't know what you're supposed to be doing, right? The first thing you should always do, right, is do what we did here, is ask ourselves, what is the problem asking me, and try to piece together which one of these methods you think is most prevalent, and then draw the diagram associated with it. And if you're really stuck and you don't know, draw all three. Draw a free body diagram, draw a state diagram, and you will get points for diagrams, right? When you don't have the diagrams, you end up losing a lot of points on things. The diagrams are really important. If you can draw the diagrams, you can write the equations, right? Notice my coordinate system, right? I'm looking at this from the top, right? So this is happening in the XZ plane for me, right? So Z plus X, so positive is never plus. Oh, nice. Okay. Let's turn this one. Any questions on diagram? No? Everybody's all right? We're good? Maybe. Stop asking me if I'm good. Leave me alone. Okay. Out of curiosity, how many people here are taking ETG 410 next semester? The PLC programming and controls class? I know you are. Yeah. Cool. It'll be fun.
Is it like this?
Yeah, so it's just this again.
Like the same materials, I just like.
Yeah, it's the same exact class. I don't even know why we have a different number for it. No, it's not like this. How early it is? How early is it? Oh, okay. I thought you were gonna tell me 7, and I was gonna be like, I don't like that. That's...
This FYI, we're all gonna be dead because we have a 7 a.m. break.
Oh, good.
Yeah, 7 a.m. to 9:30.
What class is that?
Principal design and vision.
Okay. Yeah, I mean, I don't want to. I mean, you should probably just skip that class, right?
I would. I had that in LA for her earlier class.
Yeah, that was a joke. I did not. That's not. Yeah, ETG 410. Right. So we're good with the diagram, right? So we can write some equations. We're going to write our momentum equations, right? And in this case, we're starting with the angular momentum equation, right? And remember what I told you, we are going to sum the angular momentum about the center of the rod, right? Point R here. And if I do that, these forces, these impulses go away, right? Because they're acting through point R. So these go away. These go away. All I'm left with for angular momentum is, well, I need the angular momentum of the balls here, right? So let's talk about it. I've got 2 times the angular momentum due to the tangential velocity of the ball, right? Why is it twice? Because both of the spheres are the same and they're at the same distance away from R. Okay. All right. So 2 times inside the brackets, we've got the mass of the sphere, mass of the ball, times B sub B times R ball. But because it's a tangential velocity, we can know what that is based off of where point R is, right? My distance away from the center is going to tell me what that is. And that's R times omega 1. We know omega 1. We know R1. We know the mass of the sphere. We also have the angular momentum of I sub s omega 1. Right? We were given omega 1, but we're going to have to calculate I sub s. Right? We'll talk about how to do that in a second. And what do we add to that? Well, we also have angular momentum for the rod itself, which is I sub r times omega 1. What about the final? Well, the final version looks like the initial version. It's just we're changing what the radii are and what the omegas are, right? That's what we're doing. Does everybody see how we got that from here? Are these spheres actually rotating here? Well, when compared, like, aren't these two terms the same? Right? Aren't these two terms, isn't this just double counting that? And it's not. It's not. Because this, the weight of the sphere, right? This has some distribution of mass that's going to affect how it rotates. Okay? The mass itself affects its linear contribution, right? But there's also, think about it, it wants to rotate. If you're looking at it from the top, right, it wants to rotate, wants to shake on this bar, right? It wants to, this wants to rotate like this, right? It wants to tilt on its axis. Here. It wants to go like this, right? There's a pole sticking through it. But presumably there's enough play for this to slide, so there should be enough for it to rotate slightly. Right? And that's what that I sub s omega is talking about. How is this going to rotate in this plane, like this? It's also going to actually rotate around the center, right, by that, right? So we can take this, and we're going to solve this equation here for omega 2, and we get this messy looking, well, that's actually not that bad, right? What we know most of the things in there, we just don't know I sub s, right? No I sub r was given that. I know the mass of the spheres. I presumably know the distance I am away, right? Because as it turns out, wait for it, I do, right? I know the distance that I am away from each point.
So what is the cord actually doing?
The cord is holding everything in place until some jerk comes around and cuts it with a zip. Because the whole problem starts with you're going to cut this cord for reasons. Presumably, Zach, some people just like to watch the movie. Cut cords when they see it. It's an epidemic. Really. If the cord was there, right, these things, the two balls would always be 10 inches apart, and they'd stay basically wherever you left them, right? They should end up in center. Okay, here we are. All right, so we algebra this, solve for this, right? And here we go. Is that correct? Should we have two of those? Shouldn't it be twice ms and twice is? Let's keep going. Okay. I think my algebra is wrong though, right? Okay. Yeah, no, we're good now. Sweet. That was weird. All right, and we're back. Hopefully, we never left. Here we are, right? And I think this is actually supposed to be this, right? If you actually look at the algebra here, right? So we should end up with 2 MSR 1 squared omega 1 plus IS omega 1, right? That's IR omega 1 all over, right? Well, not over, right? Yeah. Right? Yeah, so there should be a 2 though. My mistake. Change the name of the YouTube series. The Dr. D makes mistakes doing algebra. I should change it to. All right. So here we are, right? We've got this. So what do we do now? Now we go to the tables and we figure out what I sub s is. Turns out that the mass moment of inertia for a sphere is 2/5 mass times diameter squared. Right, notice I have that divided by 12 because I want everything in feet, right? And if you run this out, you get 0.00155 pound-foot second squared. And then you plug this into this equation, and you'll get this answer. Now, if somebody wants to run that through their calculator and double check it to make sure that it's right, you can. And I think that might be good, given that, my equation didn't have those 2's in it. Right? So somebody crunch this number. 2 times 2 over 32.2 plus 2 times 0.00155. I sub r was 0.251. Oh, so I forgot r squared, right? This is 5 over 12. Oh, man. That's 5 over 12 squared times 25 over 12 squared plus 2 times 0.00155 plus 0.251, whole thing times 6. What does that give us? Somebody. I didn't bring my calculator today. Apologize.
So you're putting omega. What's the IR for this?
What's IR? Is given as 0.251 in the problem statement. It is the mass moment of inertia of the rock. 0.251 pound-feet second squared. What's the number? Is it 2.0? This is what you got? So apparently I just didn't write down the right equation, but I did the correct math when I ran through this. Excellent. Jackpot. Thank you, Miguel.
Instead of zero.
Okay. That worked out in my favor. So good stuff. See you guys next time. All right. No. All right, so now we got omega 2, and that's great, and that's what we were asked to find for part A. Right? So part A done. We have omega 2. We know how fast this is rotating when the two things hit the end stop. And now what we need to figure out is how much energy are we going to lose with this plastic collision, right? So how do we do energy loss, right? This is a different question than we've been asked before, right? We haven't been asked to figure out if energy has been lost. We just kind of figure out how much we have, and if it's conserved, then we equate it to something else, right? So we're still going to use the principle of work energy, right? And so in general, in the most general case, right, I know that my kinetic energy is equal to 2 times the kinetic energy, the total kinetic energy of my sphere, right, which has 2 parts. It's got the rotational part and the translational part, and the total kinetic energy of the rod, which is only rotating. Okay, so that's in general. Do we have any potential energy here? Do we have a change in height? No. Do we have any springs? No. So we don't have to deal with any potential energy, right? So in this case, we're going to take our kinetic energy at state 1 and our kinetic energy at state 2, okay? And we're going to solve for them, right? Because I know everything that I need to find the kinetic energy at state 1. I know everything that I need to find the kinetic energy at state 2. And what I've done here, right, is I've already normalized V to be a function of omega, right? So, right, V is just omega times R, right? So I just inserted omega times R here, and then omegas come out. And if you crunch these numbers, right, you know what MS is, you know R1, you know IR, you know IS, you get 4.95 foot-pounds. At state 2, we analyze the kinetic energy as well. And at state 2, we end up with 1.71 foot-pounds. So that is a total loss of 3.24 foot-pounds of energy. You just subtract the 2. I started with, well, it's the delta, right? It's state 2 minus state 1. So I started with 4.95, I ended with 1.71. I lost 3.24 foot-pounds of energy. Where did it go, right? Where did it go? Right? Is this possible? I thought energy had to be conserved. Where did it go? It's a neat font that they have on PowerPoint now.
You remember?
Yeah. I do mind. Don't do it anymore. It's very difficult. I had to press this button on the left instead of on the right. So where did the energy go? I thought energy had to be conserved. It can't be created or destroyed, right? So where did it go? Where did it go? What kinds of energy do we have? Talked about it a little bit. Yeah, kinetic and potential, but what else do we have? There's other kinds, right? Yeah, heat. Right, heat's a type of energy. Certainly friction would create heat, right? There's also sound. When this hits the end stops, it'll probably make a sound. That's a type of energy, right? If it sparks, right, which I don't know if you guys have ever done this. When I was a kid, I had this slingshot that had some metal BBs that went with it. If you shoot it at the ground, it would spark. It's going so fast. That's the type of energy, right? That's both friction and sound and light energy, right?
So when the friction sound compared to like the air.
Yeah, air resistance is gonna eat your lunch as well, for sure.
Also, so is the unit for kinetic and potential energy, is that the same as the moment? You can hear it, but no.
Yeah. Any other questions on this one? The energy loss thing is not really right. It's more of a compare how much you had to start with and how much you have at the end, and if they're not the same, right? How much did you lose? I mean, you could pose the question another way as well, right? Like, I mean, for mechanical systems, you won't. So, right, you can't really pose the question the other way. You will never gain energy, right? By just something naturally happening, right? Your cup of coffee will never get warmer in a room that is colder than the coffee, right? It will get warmer if you add energy to it through a microwave, right? Or you heat it up in some way, but nothing will just spontaneously gain energy. It's unfortunately not how the universe works, right? And I'm pretty sure there's a class which you'll take somewhere along the line that talks about second law and things like that. I think, at least. I don't know. But I don't know. I might not. Okay. We good? Any questions? No? We talked about that. All right, let's watch the rest of this video. Oh, the online service failed. Please try again. Yes. Oh, okay. We'll do that. We'll make this work. Hit the lights first. We'll start it from the beginning. Oh. No, we were like right here. Issue?
Cycloid H.
We're like
These
that.
were the curves you make when using
Those curves.
While Adam and I built a real-life cycloid track, let's take some time to appreciate other kinds of roulettes. As mentioned before, trochoids are curves made by discs rolling on straight lines. But an epitrochoid is made when a disc rolls around the outside of a circle. Roll a disc inside a circle, and what you've made is a hypotrochoid. These are the mathematical names for the curves you make when using a spirograph tool. Notice that the holes don't lie on the circumference of the discs, though some do come close. There's a special name for epitrochoids and hypotrochoids traced by points on circumferences. Analogous to discs rolling on straight lines, they are epicycloids and hypocycloids. Now, if two circles have the same radius, a point on the rolling one will touch the stationary one exactly once, always in the same spot, creating a cusp. This cute heart-shaped epicycloid is also known as a cardioid. If the rolling circle has half the larger radius, you'll get a two-cusp epicycloid, the shape of which is called a nephroid, because it apparently looks like a kidney, I guess. 1/3 the radius gives you three cusps, 1/4 four cusps, and so on. As for hypocycloids, if the inner circle's radius is 1/4 of the largest, the resulting roulette curve is called an asteroid because it looks like a star, which the ancients also thought about asteroids. 1/3 the radius, and you've got a deltoid, named after its resemblance to the Greek letter delta. 1/2 the radius, and, well, you get a straight line. This fun relationship is called a two-C-couple, rotational motion turned into linear motion. Follow a number of points on the rolling circle, and you'll get the famous illusion where every individual point moves in a straight line, but the whole thing describes a rolling circle. Put a handle on it, and you've built a trammel of Archimedes, aka an ellipsogram, when used to make ellipses, aka a hillbilly entertainment center when bought in Osceola, Missouri. Anyway, let's get back to Avenat's curved comparison.
I have to finish.
Oh, beautiful.
Okay, there's your finish line. You ready?
I'm ready. All right, I'll count us down. 3, 2, 1, go.
Okay.
Here we go. 3, 2, 1, go. 1, 2, 3.
With
The straight was second, the straight was
the
last.
straight was last. The shortest distance between 2 points
Was last.
the slowest way to get there.
Yeah, it certainly was. Let's try it one more time, because it was super close. The brachistochrome curve was by far the winner.
Yeah.
What a mouthful of a name, by the way. Brachistochrome. Not related to the brachiosaur. I looked it up. Different roots.
I once looked up the difference between ingenious and ingenuity, and they don't know.
And they're not related.
No.
All right, I'm ready.
Okay.
3, 2, 1, go. Yeah,
Same results?
same result.
1, 2.
These are so close, it's hard to tell.
Well, we're answering the main question, which is that the brachistochrome curve is the fastest way to get it.
Well, a brachistochrome curve is also known as a tautochrom curve. It has another property that we should test, and that is, it's also known.
Look, before you get to this, we've established between these 3 curves that the cycloid main brachistochrome curve is by far the fastest.
It's by far the fastest.
Okay, great.
You get speed, and unfortunately, you get a lot of speed right away, but then you've got a lot of this little acceleration. You go straight down, and, funny enough, what you want is that perfect balance of gravity's acceleration, but also moving where you need to be. And
That's fascinating to me that geometry, which is the cycloid curve, would yield such an efficient exploitation of the forces involved.
yeah, exactly. Because if there was no acceleration, if there was just one force in the beginning, straight line would probably be fastest.
Right. Okay. What is the other quality of the tautochrom curve?
You just said it. Tautochrom means same time. So, as the geometry and math tells us, no matter where you start an object, whoops, it was my fault, but also, come on.
No, it's actually.
You guys had these tables are math. Oh, that's yeah. It's actually good. Glad I have that result. So, I'm going to remove the straight line that is possible left with a cycle, which is called a brachistochrome curve, but it also has a bizarre property where no matter where I start an object on it, when I let go, they always reach the bottom. They just get that bottom.
Wait a second. So if I started here, the amount of time it takes for this to get to the air is the same amount of time it takes for it to get to the end of the air.
Yeah, and the same from right here. Well,
Wow. Okay.
so starting from here, it's going to be tough because of friction.
Yeah.
Now, if you do this in software, it's perfect, but that's boring. This is the real world, we'll start with that.
Look, I mean, if we do 1, 2, and 3.
Yeah.
so we actually.
I feel like we could probably get much to work from here. There might be a lot of friction involved, but we can always see. We've got enough.
That's why we made 3 curves. We test this problem.
And these were all cut and sanded, clamped together, so they are incredibly strong.
I will have to, chamfer the edge as I did on this one.
Yeah.
And we're able to put some dot right and. Still will. A little bit of the fact that once you turn paper on the plexiglass, it crumbles, but way that's well.
Hey. How do you get this paper on the plexiglass in the first place?
Good question. Because it doesn't really feel glue. But there's some 3M glue.
I think this is.
I hope it will, because in theory and practice, theory and practice are the same thing. In practice,
I don't think Chicago or one of their things is. That sounds good in practice. How do you do? Like the one there.
so let us see if you do, if I do one up here, and you do one there, then, but okay, yeah, so this has got to be enough.
I think the same person should release the thing.
Okay.
Time it better.
So here, put that one here.
All right, so 3 different positions. This one has longer to go.
Yep.
This one has the shortest path. So who's gonna reach the bottom first? Well, let's see.
Intuition would say, the one in my, this one.
Yeah.
You go first, ready?
Yeah.
Dude!
Pretty good.
That was awesome!
That was so.
They all like
nice.
lit up, they line right up.
All right, let's switch it up.
Okay.
I think you're gonna have to go and release them,
Yeah.
otherwise it won't be easy to time.
There we go. 3, 2, 1. I mean, watch them lining up.
Yeah, they line up like they're waiting for each other.
Sure,
I'm gonna stand further away, because I wanna see the whole path.
Ready?
Yeah.
3, 2, 1.
How cool is that?
They totally line up at about the same period as they would for you. So given the vagaries of some extra frictions here and there, they're actually hitting this at the same sort of periodicity that they are when they start at the same point. So there's that, and then. Is this the autoclone firm demonstration?
It really is. It really is. It's also the rotation chrome, rigomite fuse, and the cycle.
So check that out.
Keep doing that, yeah. That.
Another one. Yeah, that was exactly on point.
Wow. Racia. See, in this game, no matter where you start, no matter who you are, you're always a winner. There's always a tie. So this is brain candy for me. This is something that was previously abstract and only seen in animations and in text, made real. Now I can put these wherever I want. I'm not stuck with what someone else did. I can physically hold it. That's what makes brain candy exciting.
It is like that love taking the theoretical and making it physical. And actually, honestly, we've always had what seemed to be like sister enterprises,
Yeah.
and it's nice to bring them together.
Yeah, this is a little child of ours, isn't it? Maybe one of us wasn't so good at sanding, and maybe the other of us kind of saved the day. But it's real now, and it's alive, and I think it's loving its life.
That was fun.
It was really fun. Adam, thank you so much for your help. What you do is always amazing. I hope to see all of you out there watching at Brain Candy Live. It's going to be incredible. And in your daily lives, may you always find the Totochrome, the solution that brings you and others together, even if you started in different places. And as always, thanks for watching.
All right. So the exciting conclusion, right?
But didn't they
Right. So, and in the case of a straight line, right? The only thing acting on this is gravity, right? You have mass times gravity as our force, right? But the only portion of that we see that pushes us down is mass times gravity in the x direction, right, which is defined by this angle theta. Yeah? In this case, when you've got something that's Rapistochrome-like, right, we end up having a steeper angle early on. So we accelerate, we have more of this force pointing down along the track, right? And as we go, this then levels out a little bit, right? But because we have, it's essentially, think of it this way, right? You're getting a jump start at the beginning, right? There's a larger portion of your acceleration in the direction that you want to go, right? And that's why this Rapistochrome works so well, right? And then the third option, right, which was faster than the straight line curve, was something like this, right, where we have a massive amount, we have all of our gravitational acceleration at the start, but then when we get here, we've leveled it out too much, right? So we have actually, in this case, we've got no acceleration anymore, right, because it flattens out here and just continues to go at a constant velocity. Whereas we're continuously accelerating in this case. We're continuously accelerating in this case as well, but it's at a constant angle, so we're not getting that jump start that we would normally get. Well, I thought it was a neat video. I know it's not necessarily completely relevant, but that was cool. Time is it? We got some time. Let's do one more. This is a classic problem. This is a classic bullet and block problem. So you fire a gun, right, a bullet, a .05 pound bullet is fired into a 20-pound square panel, which is initially at rest. We want to determine the angular velocity. Right? We want to determine the angular velocity of the panel immediately after the bullet becomes embedded and the impulsive reaction at A, assuming that the bullet becomes embedded in 0.0006 seconds. Okay, so we're starting with the problem. First thing we need to talk about is which one of these methods are we going to use. There's a Newton's law. What do you guys think? Are we being asked to find forces and acceleration? No, right? Is it work energy? Are we asked for forces, displacements, and velocities? Maybe. There's definitely asking of forces and velocities. Is it momentum and impulse, where I need time, force, and velocity? Which one of those two fits better, work energy or momentum impulse? Momentum and impulse, right? Because we are given time. We're given the amount of time that this process takes. The other thing is that the bullet is going to collide with the block. Right? This is a collision problem. Right? This is also a collision problem. All right. So. What do we do? We're going to draw our diagram. Well, we'll do our type of problem thing, right? The type of problem, we figured it out. We sussed it out. Is momentum, impulse. We need to find omega after the bullet's embedded. We need to find the impulsive reaction at A, right? We need to find the reactions at A. What do we know? We know the initial velocity of the bullet. We know the weight of the bullet. We know the weight of the panel. and we know the initial velocity of the panel. Okay, so P is panel, B is bullet. It gets really complicated when they start talking about, like, they call the bullet a projectile, and then the projectile hits the panel, and then you've got, what am I supposed to be using? Right? So anyway, that's not the case here. We're good. We're good, right? So these are the things that we know. So we draw our diagram, right? Here's our momentum impulse diagram. What do I have? My initial momentum in this system. I've got linear momentum from the bullet. The center of gravity of the panel will have linear momentum, but we will also have angular momentum, right? Because this is going to rotate. We start from rest on the panel, so both of these will set equal to 0, right? Plus my impulses. What impulses do I have? Well, I have those reaction forces, right? And I can't get rid of them because they're reaction forces. There's nothing else balancing them, right? The force of the bullet hitting the panel and the panel hitting the bullet cancel, but the reactions stay. So I've got a pinned connection there. Remember, a pinned connection gives me X and Y reactions, right? Because it's allowed to rotate, but it is not allowed to translate at that point. And then finally, in the final position, I've got the bullet inside of the block. Right, I got the bullet inside the block. And this whole thing is now one thing, and it will have linear momentum and angular momentum. Notice, when we came to the impulses, what did Dr. D not draw there? Dr. D did not draw the weight of the bullet or the weight of the panel. This is one of those problems where we are going to neglect the weight in terms of the impulses. And why? Well, remember, what is an impulse? An impulse is a force times the change in time. The change in time is 0.0006 seconds. 0.05 times 0.0006 is really small. 0.0006 times 20 is also really small. So we're going to say that they are negligible in this case. Okay? We good with the diagram? Remember, momentum and impulse diagrams, we draw the initial momentum, both linear and rotational, right? Plus all of my impulses, so whatever forces I have acting on here that aren't balanced or negligible. And that's equal to my final momentum, okay?
What's the 0.0006?
That's seconds, that's an S. Okay. We good with this? Everybody okay? Comfortable with the diagram? Yeah? So we're going to do our linear momentum first. And I'll write it as two equations. I'll write it as my x direction equation and my y direction equation. Why? Because remember what we're being asked for. We're asked for three things here. We're asked for the angular velocity of the plate and the reaction forces. Those are two reaction forces. Those are three total things. So we need three equations. We're going to get two of them from translational momentum, linear momentum. So the x direction. In the initial position, I have momentum from the mass times the velocity of the bullet, plus the x direction force times time is equal to the mass of everything together times the velocity of the center of gravity. And in the y direction, well, hey, I have no momentum in the y direction to start. I have no momentum in the y direction to finish. But I do have ay times t. Well, that just means that ay is 0. Right, so I found one of the reactions. One of the reactions at this moment in time in the y direction is 0. 0 pounds. Okay, remember, these just come from this diagram, right? Look at the x direction linear momentum. I've got this plus this, which is 0, plus AX delta T is equal to mg. All right, that's what I have. In the y direction, same deal. Nothing in the y direction, minus AYT, nothing in the y direction. What about the angular? Right, so for the angular momentum, I've got a couple, you got two ways that you can do it. Either sum your angular momentum about the center of gravity, which is fine and you can do it, or you sum it about point A. And I'm going to sum it about point A. Why? Because remember Dr. D's number one rule when taking moments or momentums, pick the place that has the most forces passing through it, because then you can cancel those, right? But remember, that also comes with me having to shift my I term, right? I is no longer about the center of gravity. So let's talk about it, right? I'll have MB VB naught times 14 over 12. What is that? What's 14 over 12? Yeah. What's 14 over 12? That's the distance that I am. The distance that I am away from point A, right? So the angular momentum, remember, this is saying I'm standing at point A, and this would feel like I have, the bullet is creating an angular momentum about that point, right? It's rotating around this point with a positive angular momentum of m VB0 times 14 over 12 feet. 14 over 12 feet. This is equal to what, right? Because now there's no impulses, right? There's no moment impulses because I'm summing them at point A. And this is equal to the mass of the bullet plus the mass of the panel times 9 over 12 VG, right? We are assuming now that the center of gravity has not shifted even though the bullet's now there. Okay, that is an assumption we made, right? The bullet is so light in comparison to the panel that we're going to say that that change in center of gravity is negligible. In reality, would there be a change in center of gravity? Yes. Right? There would. But for our hand calculations, it's not something that we need to take into account, right? So we're going to assume that that's now center of gravity of everything is still the original plus IG omega 2. Okay. How do I figure out IG? Well, go to my table for a panel, for a square panel. I've got 1/6 ml squared. I'll do the thing, plug in my things, I'll get this. 0.2329 feet pounds second squared. And then I'll work through this. All right, I just plug in the things that I know. Okay. Plug everything in. In this case, okay, instead of V sub G, I'm going to create an angular velocity. I'm going to say that this moves with omega 2 times 9/12, right? Because it rotates around point A, and we figured out what omega, we need to figure out what omega 2 is. Right? So we know that that velocity V sub G can be defined as omega 2 times the distance that we are away, which is 9/12 feet, right, plus 0.2329. This is an omega 2 here. Right? It's just this term. Yeah. Omega 2. If I crunch my numbers, I get 2.72 is equal to 0.5832 omega 2, where I solve for omega 2 and I get 4.66 radians per second. Take this and I put it back into the equation on the previous page that I had for A sub x. And where V sub G is just omega 2 times R. And I solve all this over here. Right? So A sub x is equal to the linear initial, or to the total momentum after, minus the initial momentum of the bullet, divided by the time that it takes. And A sub x is equal to 249.74 negative, which means it's pointing to the left. So interesting, right? An interesting result here is what? There's no vertical reaction force here. Right? There's no vertical reaction force here. All of the reaction force is trying to fight the amount of force that the bullet is exerting on the pin. Now, is that accurate? No, I mean, it would have to counteract the weight too. But we said that the weight was negligible. Right? All right. So that's a bullet in a block problem, right? There's all different kinds of bullet and block problems. There's one in your book that's really interesting. Maybe we'll touch on it. Maybe we won't. Next class, we're going to start on gyroscopic motion, which is the final topic before the next exam. Remember, this exam covers momentum, impulse, work energy, and gyroscopic motion. Those are the three things. Right? Last exam was Newton's second law and kinematics, right? So there's really three things. First problem we did today is a really good one. And I think that if you guys know how to do that problem, you'll feel like if you can understand how to walk through that one, it'll prepare you well for the homeworks. Right? And for the exam. The homeworks and the exams are from the same source. Do you guys have any questions on this one? This is just a pure momentum one, right? So how do we know when it's pure momentum versus work energy and momentum impulse, right? Well, it's all about what we're being asked to find, right? The first problem we did today with the assistive batting device, right? We needed to find the final velocity after impact, right? Final velocity after impact tells us that we need to be finishing with momentum impulse. But if we look at the momentum and impulse equations, we didn't know how fast the bat was moving to start with. So we needed to use work and energy to figure that out. So I would highly recommend when you're looking at these problems, before you even get started, take a second, think about what's being asked, what equations you think you might want to use because of what's being asked, right? Figure out if you have everything necessary to enter into those equations, and if you don't, how would you get that, right? So again, it's like Michael Scott's 100-day plan. Day 100, company is saved. Day 99, what did we do the day before the company was saved? Work our way backwards. Okay. You guys have any questions? No, that's it for me for today. We can end early. Like I said, next class. Like I said, next class, we'll be talking about gyroscopic motion and what that means. Okay. Next week on Wednesday, right, next week on Wednesday, I would highly recommend, I would very much like, let's put it this way, I would very much like that if by next week on Wednesday, somebody came up, or at least you guys started looking at problems and Like, I would start studying sooner rather than later, number one. Number two, come to class on Wednesday ready to ask questions because part of the day is going to be review. And if you guys don't have any specific questions, then we're just going to leave early, right? So I'll answer any questions, any problem you want to do, right? If you do have a specific problem before class time on Wednesday, if you could shoot me a PM, that'd be great because having time to prepare means that it's going to be more efficient, but we can do them on the fly too. Right? So. We're almost done with the semester, guys. Keep in there. Remember to get me your designs as soon as you can, so we have more time for everything. As of right now, we're still going to do the wind tunnel. Dr. Williams assured me that everything would be ready to go. I do have a backup plan just in case we can't do that. So, Logan.
For the design, does the inside have to be followed or just going over more?
So say that one more time, sorry.
So like when we 3D print, we're putting something that goes over at the bottom.
Yes. You're going to want a hole to attach to.
Last test, I think we asked you for the specific credentials for like the size of the wind tunnel, and I didn't see anything like that.
So SoundCloud, I posted an announcement. Can't be bigger than 10-inch diameter.
Okay.
Yep. 10-inch diameter gives us enough clearance. That gives us a little play on either side. But if you keep it at 10, no larger than 10-inch diameter, you'll definitely be good. Thanks, Kilo. Take it easy.